Last time we were talking about gravity, and so we should continue doing so. So we finished last time, and I explained that even if you throw a ball 10 kilometers vertically, that the force on gravity is microscopically close, or only microscopically changes. And I said, well, even at the ISS, even at the altitude of the International Space Station, which is 400 kilometers up, the force of gravity on that space station, on the astronauts on that space station, sorry, the acceleration due to gravity, is still relatively close to what you experience on the surface of the Earth. And so you could go and you could compute that. In order to do so, you would, when you're calculating the force of gravity, instead of substituting in the radius of the Earth for the distance between the two objects, you would substitute in the radius of the Earth plus 400 kilometers. Then you would solve, just do the arithmetic, and you'd end up with 8.68 meters per second squared. Now the question, that's maybe 10% less, 15% less than what we experience on Earth. So the question then is, aren't the astronauts in 0G? I'm going to put that in air quotes. And yet, they still feel 89% of the Earth's gravity on the surface. So what does that mean? Like, in what sense are they in 0G? How are these two ideas congruent? So this requires a detour into this thing called free fall. So our goal today, well, one of our goals is going to be to try to explain this seeming incongruence. So let's consider a different scenario. So suppose you jump on a trampoline. Suppose you jump on a trampoline, and just after you leave the mat, on your way up, of course, you drop your phone. So we have the tools to now understand and try to analyze this situation. Let's do that. Let's answer the question: what happens? Like, what do we observe? So initially, here's a trampoline. Here's you. You have some initial velocity upwards because you jump up and then you're headed up, and then you drop your phone right after you are on your way up. And so now you're on your way up, you have that initial velocity, and now there's also your phone that has that same initial velocity, right? Because it was traveling, unless you threw it downwards, if you just let go of it, if you just dropped it, its velocity wouldn't change. So it would have the same velocity that you do. So the phone has the same initial velocity and the same downward acceleration, because you both experience the pull of gravity, as you do. Now, there might be some difference because drag doesn't act on everything equally, but ignoring air drag, both of these statements are true. And so the vertical position of the person that's jumping would be, we have the equations for this, it's just the standard kinematic equations. It'd be V naught, or let's say VI, minus 1/2 GT squared. And similarly, the vertical position of the phone as a function of time, well, it has the same initial velocity, it experiences the same pull of gravity downwards, and so it has the same functional form. And so importantly, the height that I'm at is at all times equal to the height of the phone. And so from my perspective, the phone moves neither up or down. The phone doesn't move, it just floats there. And that's because I'm moving with the phone. And so this is what we call, like from my perspective, both the phone is floating in 0g. But really, neither of us are experiencing zero or no gravity. Instead, we're experiencing something called free fall. And so what free fall is it's just what it is the experience that we have. It is the phenomenon that occurs when an object is just under the influence of gravity, right? So another example of free fall would be like just dropping a brick off a bridge, right? That brick experiences free fall. And importantly, let's say that we can neglect drag. Let's say you and a brick are both dropped off of the Empire State Building. And there's a trampoline at the bottom so you don't die in Minecraft. As you're falling, the brick will just appear to be floating in the air. If you closed your eyes, or if you somehow could only see the brick but couldn't see the world around you, it would just look like the brick's just floating there and you're just floating there. So because in those situations, only the influence of gravity is at play here, the experience of the person and the phenomenon that's occurring for whatever object, those are both experiencing free fall. They're undergoing free fall. So let me give another example. This one I'll write out. So do you guys remember when we had that archer question where the archer was sitting on the ground and shooting an apple at a tree and they had to aim directly at the apple? So that was an example of free fall. So just to make this a little bit more clear, let's modify the situation a little bit. Let's suppose that the archer was initially level with the apple. So the picture would be something like this. You have the archers on some sort of stand. How do I draw a stick figure holding an arrow or a bow and arrow? That's pretty good. And it should be aimed directly to the right. Come on, I don't know why I'm spending so much time on this, but I want to make it look good. And then here's your tree, really big tree. And then you have your little apple here, right? So in this situation, or in the assignment, so the archer was supposed to aim directly at the apple, right? And perhaps now it's kind of clear why that has to be the case. And that's just basically because both the archer, or both the arrow and the apple experience the same downward acceleration. But in this case, maybe it's even more obvious. They both have the same initial vertical position. They both have the same initial vertical velocity. In particular, it's downwards with the initial velocity is 0. And they both experience the same acceleration. So in this case, it's still true. The archer just aims at the apple. Right as the apple falls, the arrow will also fall at precisely the same rate. And the vertical positions of the apple and the arrow will go down in accordance with each other. And so the point that I'm making here is that the horizontal motion of the arrow doesn't affect the fact that the arrow is in free fall. That. So the reason this is the case is that the only acceleration that the arrow is feeling, well, okay, let me rephrase. Suppose that there were no gravity, right? The archer would shoot directly at the apple. The apple would fall, but it wouldn't move, and so the arrow would hit the apple. Now, if you turn on gravity, both the arrow and the apple experience or fall at the same rate, and the apple is experiencing free fall. So in that sense, the arrow also is experiencing free fall. It's just moving while falling. That would be like taking a running jump. You're still experiencing free fall. You just happen to be moving horizontally while you do it. And that's an important point. A thing can undergo free fall even if it's moving horizontally. In fact, a thing can be experiencing free fall even if it's on its way upwards, like in the phone example. From the moment you left the trampoline, you and the phone are both experiencing free fall, even though you're headed upwards. And that's because the acceleration that you experience, the only force that you feel is gravity. Now, just as a separate consideration, what would have to happen in order for the arrow to hit the apple before the apple hits the ground? Well, your intuition should say that you have to fire the arrow sufficiently fast, right? If it's too slow, it'll still hit it. If it's too slow, then the apple will hit the ground before the arrow does, or before the arrow hits the apple, and so the arrow will end up short. If you push the tree further and further back, though, you have to fire faster and faster to keep up with that distance. And so this is actually a common theme. If you want to achieve something that requires motion that's further and further away, you have to initially be moving horizontally faster and faster, and that should line up with your intuition. But it also will help explain what the astronauts are experiencing. So now let's look at a more, oh, dare I say it, canonical example. So this is a thought experiment known as Newton's cannon. Pardon the pun. And no, that pun was 100% intentional. So Newton's cannon is just a thought experiment. I don't know if Newton actually came up with it, but it's just a way of imagining what happens in the extreme. So first, we have to consider, or we have to realize, that the Earth is round. Right. So don't get me started. If you want to be a flat earther, you're welcome to be a flat earther, but you're not welcome to stay in this class. So the Earth is round. Actually, even a flat earther would say the Earth is round. They just think it's like round like a disc, right? Anyway, so the Earth is round, and so you can't just keep pushing this tree back forever, right? Because eventually the tree will, like, just to draw a little picture, eventually here will be the archer, not to scale. And then the tree will be like way over here, right? So eventually it doesn't make sense to aim directly at the apple, right? And that's because of the curvature of the Earth, right? Like the orientation of objects, and straight lines don't become straight lines. So what happens if you fire a cannonball horizontally? So I'm just going to draw a picture. I'm going to do my very, very best. So let's say that you have a giant cannon, right? Let me draw this a little bit better. Giant cannon, right? Aimed perfectly horizontal. So if you zoomed in, it would just look like, here's the flat Earth, and then here's your giant cannon. It's just aimed perfectly horizontally. So if you fire the cannonball, what happens? Well, at least on a small scale, you fire the cannonball comes out, and it goes like that, right? Follows the trajectory. So on a small scale, it just ploops out, right? Now, if you fire the cannonball a little bit faster, it'll go a little bit further. But as it's traveling, the direction of the force on the cannonball actually changes directions. Initially, the direction on the force is downwards, towards it's towards the center. But gravity is a central force, and so if the cannon, say, made it to here, the gravity will be in a slightly different direction, but it'll always be perpendicular to its travel, or it'll always be downwards towards the center. So if we fired it a little bit faster, what would happen is it would go out a little bit further, right? But the important point is that from the cannonball's perspective, it always feels the force mg downwards, because downwards just means directly below the cannonball, which is towards the center of the Earth. Now, what happens if you fire the cannonball just a little bit faster than that? So it's still perfectly horizontal, but now it goes even further. And because it's going faster, the amount of time that it would take to fall and hit the ground is enough time to cover a larger distance. But if it travels a larger distance, the Earth curves away more. And so, in fact, there is a speed, not terminal velocity, there is a speed that you can fire it that in the time it would take to go all the or halfway around the Earth, the Earth's, or the distance that it travels around, or the distance that it would have fallen in that time, the Earth has fallen out from under it. And so in that case, the cannonball will just hit the cannon in the back. So the point is because you're, as we fire the cannonball faster and faster, the cannonball is always experiencing the same downward acceleration. And it always drops the same distance in the same amount of time, or from the cannonball's perspective. But from the Earth's perspective, the cannonball is turning. And so the distance that it travels, the distance that it falls, might be the distance that it actually falls relative to from the Earth's perspective, might be less than the distance that the cannonball falls, because the Earth has curved out from under it, right? The Earth is round, so if the Earth was flat, regardless of how fast you fired it, it would always fall the same distance in the same amount of time. But because the Earth is its rotation, it moves away from the cannonball's trajectory, there is a certain speed that the cannonball's trajectory, can keep up with the rate at which the Earth curves out from under it. And so what happens is once you reach this critical speed, the cannonball just stays the same distance away from the center of the Earth. So this is all to say, at sufficiently high speeds, actually, I don't need it. I've just summarized that in words. There will be some text about this that's in the lecture notes, but this phenomenon where we have the cannonball moving sufficiently fast that the Earth drops out from under it, this phenomenon is called orbit, as correctly guessed or suggested by Cesar. And so the point is there was no difference between just firing a cannonball and it just falling and orbit. The only difference was the initial speed. And so we can say that orbit is just an extreme version of projectile motion. Keep in mind, well, okay. So remember that, as we discussed with this Archer and Apple example, the horizontal motion of the object didn't actually affect the fact that it was in free fall, right? Regardless of how fast you're firing the arrow, it's still in free fall the whole time it's traveling. And so is the cannonball. Even in the moment when you have fired the cannonball so fast that it can go around the Earth in the time it would take to fall to the surface of the Earth, which would be orbit, even in that case, it's still experiencing free fall because the only force it's experiencing is gravity. So now let's go back to those astronauts aboard the ISS. Because we wanted to understand how they can be experiencing 8.78 meters per second squared of gravitational acceleration while at the same time being in 0g. So the point is that the astronauts are just experiencing projectile motion. And projectile motion is just free fall, assuming the projectile motion is caused by gravity. And the point is just their initial velocity Exactly, they're perpetually falling but never hitting the ground. Their initial velocity is just big enough that they never hit the ground, exactly it. And so thinking back to the example with the trampoline, this person was experiencing free fall while they're going up and on their way back down. And so that's why it seemed like the phone was just floating in front of them. It was just floating there in 0G. That's what it's the exact same phenomenon that the astronauts experience on the ISS. It's not that there's no gravity, so things just float. It's that everything is experiencing the exact same projectile motion. So, like in the trampoline example, imagine instead of being on a trampoline, you just launch off the trampoline really fast horizontally, and then you drop your phone. Well, if you stay in the air long enough, if you get enough hang time, you could just play with your phone as if it were just floating there like the astronauts do in the videos that they send down. And that's all that's happening for the astronauts. They are just, they're falling, but everything else that's in the space station is also falling with them. And so it seems like everything's floating. And the reason why they don't hit the ground, like this person on the trampoline does, is because they're falling, but moving horizontally so fast that they miss the ground. The ground curves out from below them before they can hit it. So the term 0G is actually really, I actually really don't like it, because it implies that there's like zero acceleration. And that's precisely not the case. When you are in 0G, you're actually in 1G. If you want to get formal and give like a consistent definition of how many G's you're experiencing, what you would do is you would find assuming you're under the influence of some gravitational force, the Earth's or the moon's or whatever, you would figure out what the net force on the object is, and then subtract off the gravitational force. And then and then divide by your mass to get the acceleration that you feel. Yeah, no, that's actually a really good word for it. The acceleration that you feel is the amount of G's that you feel, basically. So yeah, normal forcelessness is actually a good word, because the reason for that is because when you are sitting on your chair or standing up or whatever, you're not feeling the force of gravity. What you feel, the weight that you feel, is the normal force pushing you up. If that normal force were there, you would feel like you're floating. And so if you want to figure out how many G's you experience, just subtract off how much gravity you have, how much the force of gravity is on you, and then that will tell you how many G's there are. For an astronaut, it's 0 because they only have the force of gravity. They don't feel they're accelerating. No, so the only acceleration that you feel is acceleration that is not from gravity. And actually, there's a deep reason for that, and we can talk about that after lecture if you guys are interested, but we should probably proceed. What if they're orbiting around a planet with a really small radius? They still wouldn't feel their acceleration. Well, okay, let me rephrase. Depends on how small the planet is. There are things called tidal forces, which, depending on the size of your orbit, can make you feel like your feet are accelerating faster than your head, for example. This is actually called spaghettification. But let's talk about that after lecture. It's a really interesting topic, and I'd love to talk about it, but we have a lot to get through. So we can put this another way. If an object is experiencing only gravity, then at the instant in time when the object is moving horizontally, we can we can imagine this thing called the Circle of Oscillation. So this is just another way to understand gravity. So imagine an object is undergoing projectile motion. So at the top of the arc, we could draw this as, so it's a parabola. This is just normal projectile motion that you guys are used to. It's just like normal parabolic motion. So at the top of the arc, the object is moving only horizontally, right? It has no vertical motion, because that's what it means to be at the top of the arc, moving with some speed v. And the whole time, the force on it downwards is F, right? And so we know how to characterize the magnitude of a force when your velocity is perpendicular to your force, right? That would be a force caused, or a force that's causing the centripetal acceleration. And so we can actually figure out what type of circular motion that would be by drawing this thing called the Circle of Oscillation. Now, the Circle of Oscillation, I believe oscillation in Latin, or it comes from the Latin root for like kissing. It's basically the kissing circle, i.e. it's the circle that kind of just kisses the parabola, right? It kind of matches the curvature near the point. And so this circle here that I've drawn, this is the Circle of Oscillation, and you can always draw a circle of oscillation at any point, but at this point it's interesting. And this radius we might call the radius of oscillation. By the way, it's not oscillation, it's osculation, different word. But so at this very instant in time, the force it feels points towards the center of the circle. The velocity is perpendicular to that, or is tangential to that circle. And so we can use centripetal acceleration to figure out how that force relates to that velocity and relates to the radius. So the radius, our osc, solves the equation. Well, it's centripetal acceleration. So it would be, the force has to be equal to the mass times the centripetal acceleration. M times v squared over r osc, right? So that's just m times v squared over r, which is the centripetal acceleration. That just has to be true because its velocity is tangential to the circle and its force points towards the center of the circle. And so if an object is near the Earth, the object is near the surface of the Earth, then we know that the force is actually just equal to mg, right? And so we can plug that in and solve and find that the radius of oscillation is just v squared over g. So now, why do we care about this? Well, as the horizontal velocity of the object increases, this radius of oscillation increases, right? And in particular, as the radius of oscillation increases, the distance that the object travels, i.e. like the length or the horizontal length of the parabola gets larger and larger. And it turns out that if the radius of oscillation is equal to the radius of the Earth, then relative to the ground, because the ground traces out, the ground would trace out that circle, relative to the ground, the object always moves horizontally. And so this is just orbit. And so this is an easy way to figure out the orbital speed, for example, near the surface of the Earth. And you'd have to adjust it depending on what the acceleration that you should feel is, but this is a way to do it. So the way to think about this is like, come on, scroll, is like, so you have your Earth, and then you have your projectile, right? You have your projectile, it's just launched like this. So at the top, there's a little baby circle that tells you your radius of oscillation. But if it goes faster, then like this part of the parabola gets less steep. And so this circle of oscillation gets bigger in order to stay a kissing circle. So if instead we had like a projectile motion that was like this, really fast horizontally, then that circle of oscillation is larger. And that's actually like a really poor drawing. It'd be something like this. It's hard to do. But the point is, not quite. It's just another way of explaining why orbit happens. But the point is as your speed increases, that radius of oscillation, which is the radius of the circle of oscillation, gets bigger until it's literally just the whole Earth. And then, of course, your motion will always be horizontal. Could the velocity ever be too much to break the orbit and leave orbit tangentially? Is that how we launch rockets to space? Actually, yeah, that's not how we launch rockets. That's how we launch rockets to other things that are not the Earth. Like when we launch a rocket to orbit the Earth, it's still just orbiting the Earth. But if we wanted to get to Mars, then yeah, we have to do that. The moon is still orbiting the Earth, so. But yeah, and again, we can talk about that more after lecture. It's very interesting. Orbital mechanics is super interesting. Mars isn't orbiting the Earth, so that would be a good example. So now we kind of have to change gears. So hopefully you guys at least have some sort of intuition for orbiting. Basically, if you go fast enough, you miss the Earth as you fall. And that's all orbiting is. It's just projectile motion, but going really, really fast. Now, we can start doing a lot of math with projectile motion. By the way, we're going to go about 10 minutes late like we usually do on Wednesdays. And so we're going to take a trip back in time about 400 years, even before Newton. Newton was like 1700s, late 1600s, early 1700s. What we're about to do is talk about Kepler's laws, which were written down by Johannes Kepler between the years 1609 and 1619. And so this was like 60 years before Newton, I think. So I just want to remind you that a law is an empirically derived phenomenon, meaning they observed, whoever created the law or whoever wrote down the law, observed what happened in nature and then just used those observations to write down basically a formula or come up with an idea that matches those observations. And then hopefully, if that law is good, it will match other observations that you haven't made yet. But importantly, these are phenomena, or these are empirically derived formulas that's not how you spell formulas. Formulae that fit the data. And that's important. They wouldn't have, so what this is not, a law is not, you come up with an idea and then check if it fits the data. It's you look at the data and then you see what sort of equations or what sort of mathematics does or would accurately describe that data. That's what a law is. A law is not a model. A model is it's a conceptual idea that you can then combine with laws to get an understanding. But the point I'm trying to get is that Kepler's laws don't promote any understanding of why these things are the way they are. It's just a description, not an explanation. So Kepler just looked at the stars, looked at the planets through telescopes and so on, and then he just figured out these relationships. So let's start with the first one. So Kepler's first law. I don't know why, but these always come in threes, like Kepler's laws, Newton's laws. So Kepler's first law is the statement, and I'm going to have to copy this word for word because I want to get it right. So the paths of bodies trapped in orbits form closed ellipses with the gravitating body at one of the foci or foci. Right, so this law was first shown by Kepler, showing that Mars has an elliptical orbit. That was something that had never been done before, and we now know it's true. It's only very slightly elliptical. It's almost perfectly round or perfectly circular, but it is a little bit elliptical. Okay, but there's a lot of things in this phrase that you might not remember from geometry. So let's do one of those recalls, the geometry of an ellipse. So we have to do a lot here, because I imagine that most of you guys don't remember anything about ellipses. So I'm going to do my best to draw an ellipse. So bad. Okay, now let me just invert that. I think I can invert it. Paste. Rotate. Flip vertical. It's not perfect, but it'll do. All right, here's an ellipse. Drawing these things. So so here's the center of the ellipse. This distance here, this is called the semi-minor axis. It's a distance. This distance here, oops, this is called the semi-major axis. And this distance is used pretty frequently, so we give it a name, we call it A. Now there are two special points in this ellipse. One of them is around here for this ellipse. Another one would be around here for this ellipse. Now this is not technically an ellipse because it's like, it has a sharp corner here. But if I had drawn it perfectly, these 2 points would both be foci, or the singular of focus. This is a focus of an ellipse, this is a focus of the ellipse. Every ellipse has 2 foci. This distance here, that distance can be written in terms of EA. So E is a number, it's not Euler's number, it's not 2.718, it's just a variable. And A is the semi-major axis. And so this variable, E, this is called the eccentricity. So the eccentricity basically tells you how round is the ellipse. So with an eccentricity of 0, that would mean that this distance here is 0 from the center. And so that would make our ellipse a circle. So E equals 0 implies we have a circle. And that's just because it makes the 2 foci come together. Now, by the way, just as a reminder of how ellipses work, one of the ways that you can draw an ellipse is by, like, if you wanted to do this in, like, with a pencil and paper, is you would put like 2 pushpins is how round the ellipse is. So an ellipse can go anywhere from like really, really not round to very round, right? So it's just how round is the ellipse. So the reason why these foci are special is because if you add up the distance from one focus to a point plus the distance from the other focus to that same point, that number is always constant. That's what makes the foci special. And so that sum would be the same as if it were here. And so there's only 2 places where that happens. And that's, so one way that you could say draw I'm gonna erase that just so it doesn't clutter. One way that you could draw an ellipse is by putting 2 push pins into a piece of paper, like, you know, one of these guys. That's a pretty good push pin. Not a great artist, but I'm kind of happy with that. If you put like 2 push pins down and then you tied a string kind of loosely around them with like a little bit of wiggle room, and then you put your pencil here. And then you just trace out an ellipse. And the reason why that would work is because this distance is always constant. It's always the it's always the distance between the that distance would always be the distance between the 2 push pins. And then the other distance would be held constant because the string has a fixed length. And so it would draw out an ellipse with these 2 push pins at the foci. This is, and you can like look up on YouTube drawing an ellipse tutorial or something like that, and it'll do precisely this method. And it relies on the fact that the distance from one focus plus the distance to the other focus is always the same for an ellipse, for any point on the ellipse. Now, that's great. That's how you draw an ellipse, and that's why those foci are special. There are other reasons why they're special too. But the important point from Kepler's first law is that the gravitating body, the thing that's actually doing the that's causing the gravitational force, like think the sun because the Earth orbits it, so the sun is the gravitating body. In that case, the gravitating body is always located at one of the foci. And then the body moves around, or the thing that's doing the orbiting takes the path of the ellipse around that focus. So I need to introduce some more terms. So regarding solar orbits, which are orbits about our sun, by the way, our sun has the scientific name Sol, S-O-L. The aphelion of an orbit, it's just a random technical word that you'll have to learn, is the point in the orbit furthest from the sun. So if you want to describe, so put plainly, aphelion means, like, if the Earth is at aphelion, that is the furthest the Earth will get from the sun. Perihelion is the point in the orbit closest to the sun. Closest. So if the sun were at, say, this focus, then aphelion would be over here, perihelion would be over here, right? So we can actually describe the shape of an ellipse mathematically. Really easily. There's a whole bunch of different ways to do it. But we're going to use one particular way. So we want to be able to give a formula. Let me draw a picture really quick. So, God, I'm so terrible at drawing ellipses. So let's say that we have a focus here. Maybe that's the focus that we put our, like, the sun or the Earth or whatever at. We would like to be able to give this distance r in terms of this angle theta. So as theta goes around, we'd like to be able to say how far away the orbit is, or the point on the ellipse is, from the focus. And so the formula for this is just given. It's just, I can just give it to you. It's r of theta is a. Remember, a is the semi-major axis. It's basically half the length of half the larger axis length, hence semi-major, times 1 minus e squared, e being the eccentricity, divided by 1 minus e times cosine of theta. And so actually, you could go and you could check what happens when e is 0. If e is 0, that means it's supposed to be a circle, right? Let me actually put this slightly further down so I can put a box around it. So what happens when we plug in e equals 0? Well, then we would get that r of theta equals a divided by 1, or it's just a, right? And so when the distance from a point doesn't change regardless of what angle you're at, that's what a circle is. A circle is a set of points that are all equidistant from a center. So it's just more evidence that when the eccentricity is 0, you get a circle. And by the way, when the eccentricity is 0, that means that the two foci, or as the eccentricity goes down, the foci get closer and closer together until when eccentricity is 0, they overlap. Now, I told you that this is a law, Kepler's first law, so I should probably qualify that statement a little bit. So it's pretty good for the solar system, it turns out. But there is one caveat. Gravity is a two-way force, right? We know that. And so what that implies is that the planets tug on the sun. So that would imply that the sun should also experience some sort of elliptical orbit. And so it would be more correct instead of just saying that the gravitating body, because there's not just one gravitating body, it would be more correct to say that the center of mass of the system of the two bodies is at one of the foci. So rather than just putting the sun stationary at a foci, at a focus, and then having something going around it, technically what we should do is we should figure out where the center of mass is for the two objects that are pulling on each other, put that center of mass at one of the foci, and then both of the objects will have their own little ellipse that goes around that focus. Now, because the sun is so much heavier than everything else in the solar system, only a few, I think actually only Jupiter, only the Sun-Jupiter system has the center of mass outside of the sun. Like if you figure out where the center of mass is for the Earth-Sun system, it's just slightly away from the center of the sun, because the Earth is just so light, it just has so little mass compared to the sun. So the sun really doesn't move a whole lot for the inner planets and for the lighter planets. For Jupiter's extraordinarily large compared to the other planets, and it's far away. So the center of mass for the Sun-Jupiter system is slightly outside the, I believe it's slightly outside the sun's surface. And so the sun actually does go in a little orbit around that focus. All right, so we still have more to talk about, but we can save that for Monday. Let us stop